A very good afternoon to all of you. So we are starting the fourth lecture in this functional materials series today, and we'll be continuing from where we left off in the last class, and we'll cover a little bit of the following portions, as you can see over here. Which I'll be covering today will be cell characterization. A part of the cell characterization we had already covered. If you remember, CV and all we had covered in the last lecture. So today we'll continue with that, and we will be talking about a very important technique, which is impedance spectroscopy. Then we'll have a little bit discussion on the life of a battery. Then with that, we'll complete batteries and we'll move to supercapacitors, where we will discuss about electrochemical and double layers capacitors, pseudocapacitors, as well as hybrid capacitors. And then we will be discussing the concept of fuel cells. So this is basically the overview of the class lectures what we have today. So coming to electrochemical impedance spectroscopy. So please understand that this electrochemical impedance spectroscopy, it is a non-destructive technique, and this is basically an in situ analysis of the dynamic processes which are occurring inside the battery or inside the cell. So when you are actually charging and discharging a battery, quite a few dynamic processes are occurring. And this EIS or electrochemical impedance spectroscopy is a technique by which actually you can find out what are these different dynamic processes which is occurring inside that particular coin cell, and a pack of these coin cells we call is at a battery. So it provides a considerable amount of information in a relatively short space of time, and it preserves the integrity of the battery. So you need not decrimp or you need not disassemble the battery and then check what is happening inside. So as and when the processes are running, you can test it using this electrochemical impedance spectroscopy. So what do you do in case of EIS? You have a small AC signal which you are applying over a very wide frequency range, and then you are measuring the response. So please remember, this EIS is particularly sensitive to systems that contain several impedance elements. So you can have bulk components and interfaces. So it makes it very well suited to study multi-component device such as a battery. And understand this thing that different components and processes within a cell, they are operating on different time scales. So they have different time constants, and this can be separated in the frequency domain using the electrochemical impedance spectroscopy. So if you look into the right hand side, I have shown you how a Nyquist plot, this is what we say a Nyquist plot of the EIS, this is how it looks. And the equivalent circuit, which is going to, if you model this particular plot, then this is the circuit which is going to resemble this particular output in the EIS spectra. So this is an idea which I have shown over here, and how we are getting this is what we are going to discuss in the next few slides. So now, what are these different processes which are taking place inside the battery? So there are very many processes are going on, and there are quite a lot of degradation mechanisms which takes place in the battery. Why EIS is important? Because whenever I'm testing a new material for the battery, in that particular case, you need to know that how efficient that material is, and to check the efficiency of that material, you need to know what are the pathways by which the degradation can happen. So let's look into a few of these degradation techniques. So one, what you have is the electrolyte decomposition, which can take place. So the effect is going to be, if the electrolyte is decomposing, there's going to be loss of alkali metal ion, and there is going to be a deterioration in the ionic transport, because you're losing electrolyte and you're also losing, if you're having a LCO graphite kind of a lithium ion coin cell, in that case, what you're losing is your precious alkali metal ion, which is the lithium. So obviously the capacity is going to fade, and the resistance is going to, or resistance or impedance is going to rise. Similarly, if you have another degradation mechanism is the SEI formation. So again, the same thing. If your electrolyte is decomposing, it is going to form SEI. If it is forming SEI, then again you will find capacity fading and impedance rising. Then you can have, you're using binder materials. Apart from your active material, when you're fabricating the electrode, what you are doing, you're using PVDF binder, or you're using CMC binder. Along with it, you're having some conductive carbon being added. So this binder can also decay in the presence of all these mechanisms and in the presence of the electrolyte. So again, you will find a lot of capacity fade and rise in the impedance. Similarly, you can have particle contact loss. Because of this SEI formation, there's going to be cracking on your electrode surface. And if the electrode surface is cracking, in that case, your particle contact loss is going to be there. Again, you will find a lot of capacity fade and impedance rise. There's going to be particle contact loss also. It's going to be the same result. Then you can have metal plating. What is going to happen that the lithium which is moving in from the LCO and it is depositing itself during the process of charging, when it is depositing itself in between the layers of carbon layers of the graphite, some of it can also get plated on the graphite surface. So then what is going to happen is going to be loss of alkali metal, so your capacity is going to fade. Transition metal dissolution can happen. As I said, that if you are using cobalt, if you're using manganese, in all these cases, suppose if you have a spinel electrode, in that case, there can be a loss of manganese. As I said, that Mn3 plus is going to kind of degrade into Mn4 plus and Mn2 plus, and that Mn2 plus leaches out into the solution. So in that case, in those kind of electrodes, this transition metal dissolution is going to happen and you will see capacity fading. Then, of course, there can be changes in porosity, there can be decrease in the electrode surface area, oxidation of conductive additive, whatever you're adding, and there can be current collector corrosion. You have this current collectors over there, which are copper and aluminium, and so these can also deteriorate. So all of this is going to have an effect on the ionic transport, and the moment your ionic transport, there is a problem, immediately there is going to be a rise in the impedance. So these are all these various mechanisms of degradation in the battery. So it looks like that, it's only charging and discharging, but internally a lot of processes are happening, and in every stage there is a chance of degradation happening. So EIS can give you an idea about all these different mechanisms which are occurring in the battery. So let's see, first we have to now revise that what exactly is impedance resistance. So Ohm's law is defining resistance in terms of the ratio between the voltage and the current. So R is equal to E by I. Now please remember this relationship is limited to only one circuit element, which is the ideal resistor. So now ideal resistor has several simplifying properties. What is that? It will follow the Ohm's law at all the currents and voltage levels. Its resistance value is independent of the frequency, and the AC current and voltage signals through the resistor, they are always in phase with each other. So this is when you're talking about ideal resistance. But in real life, it doesn't happen. In the real world, what is that? The circuit elements, they have a very, very complex behavior. So instead of resistance, the term what we use over here is impedance, which is a more general circuit parameter. So like resistance, impedance is the measure of the ability of a circuit to resist the flow of electric current. Unlike resistance, of course, impedance is not limited by the simplifying properties which I have already given in the previous slide. So electrochemical impedance is usually measured by applying an AC potential to an electrochemical cell, and you're measuring the current as it is flowing throughout the cell. So suppose you are putting in a sinusoidal excitation. So the response to this potential is going to be an AC current signal, and this will contain the excitation frequency and as well as its harmonics. So this current signal can be analyzed as a sum of all these sinusoidal functions, which is nothing but a Fourier series. So now electrochemical impedance is measured using a very small excitation signal. And this is done so that the response which you get from the cell should be pseudolinear. So what happens is in a linear or a pseudolinear system, which is like pseudolinear is tending towards linear system, the current respond to a sinusoidal potential. This is going to be a sinusoid at the same frequency, but what you see is there is going to be a phase shift. So that is very important. So this concept is very important. So what is happening now? This excitation signal ET is equal to E0. Oh, sorry, this is written as cos, but it is sine. So E0 sine omega t. So ET is potential at the time t. E0 is the amplitude of this particular signal over here, and omega is the radial frequency. And omega, is equal to 2 pi f, where f is the frequency which is expressed in hertz. Hertz is nothing but per second. So this is the sinusoidal current response in a linear system. So you are applying these kind of a potential, and the resulting current which you get, it is going to have a phase shift. So how do you measure this impedance? So you generally use something which is known as a frequency response analyzer, and this is used in combination with an electrochemical interface. So the electrochemical interface will apply a constant voltage or a constant current, and the FRA or this frequency response analyzer is going to superimpose an AC signal. And a multiplexer will connect this particular FRA to the battery test system, as you can see over here. So the battery is connected using 4 different wires. 2 are for the current flow, as you can see over here, and 2 are for the voltage. So the FRA will output a signal to the cell via this counter electrode, and the signal is returned through the signal will be returned through this working electrode, the I+. So it is coming, the signal to the cell is sent via this counter electrode, this I-, and it will take it back through this working electrode. And it will also connect a pair of reference electrodes, as you can see over here, that V plus and V minus, and this will measure the voltage across the cell. So the FRA is going to apply a small AC signal, usually in the range of millihertz to megahertz, and it will measure the response of this particular battery to it. So now please understand this EIS you can use either in a potentiostatic, that is constant voltage, or a galvanostatic, which is a constant current mode. Okay. So potentiostatic mode is where a voltage is applied at each frequency and the resultant current is measured, and this is the most common way in which you are recording EIS. The current will respond at the same frequency as the applied voltage, but it can be shifted in phase. Now, in order to ensure a steady state, this EIS is usually carried out with a small potentiostatic signal amplitude of 10 millivolt, so that the cell response is going to be pseudo-linear or in phase. And if the system is non-linear, the response is going to contain harmonics of that input signal frequency, whatever you have used. So if you have to accurately perform EIS on a cell when it is cycling, so what you have to do is you have to give a rest period before you start the measurement and also a rest period after you start the measurement, so that the cell voltage will not vary significantly during the measurement. And along with it, the cell can recover also from any changes which occurred during that EIS run prior to continuing with the constant current or the constant voltage mode cycling. So that is very important. So you have to give a small rest period before you start the measurement and a small rest period after you complete the measurement. So this particular slide is covering all that I have already discussed in the previous slides. So please understand that in a linear system, the response signal or this IT is shifted in phase phi and has a different amplitude than I0. So IT, whatever is the signal which is coming out, the current which you are getting, is now a function of I0 sine omega t plus phi. The sine omega t was originally which was there, and this phi is basically nothing but the phase shift. So now what you get is an expression which is analogous to Ohm's law, and it will allow us to calculate the impedance. So impedance is given as Z. So ZT is ET by IT, and this is nothing but, as you can see over here, E0 sine omega t by I0 sine omega t plus phi. So ultimately E0 by I0 you can give as Z0, and this is nothing but sine omega t by sine omega t plus phi. So the impedance is therefore expressed in the terms of a magnitude Z0 and a phase shift phi. So this is an important concept. Now you know Euler's relationship, that is e to the power j phi is equal to cos phi plus j sin phi. So this phi is a real number and j is an imaginary unit. And so you can express this entire impedance as a complex function. So if you go into this complex numbers is zt is given as z0 cos phi plus I sin phi. So please, this is regarding refreshing your ideas about this Euler's theorem. So impedance is Z is equal to V by I. So you have this equal to Z0 e to the power j phi. So ultimately what you have over here is Z prime plus JZ double prime. And this J is nothing but root over minus 1. So the generated impedance spectrum which you have, it will consist of both resistive as well as reactive components. And the resistance is made up of a combination of all these electronic and ionic resistances. The most common form in which you are plotting this EI spectrum is the Nyquist plot. So what you do is, it is a Z star complex plane plot. So where Z double prime against Z prime is plotted on linear scales. And if you present your data in this way, it basically displays the resistance along the real axis or the x-axis and the reactance including the capacitance along the imaginary or the y-axis. So please remember, what you are doing is you are displacing the resistance along the real or x-axis and the reactance or capacitance along the imaginary or y-axis. So when you look into this plot, now it will get a little bit more clear to you. So what you have over here is, on your x-axis is the real z, on the y-axis is the imaginary z. This is known as z prime. Sorry for this interruption. So there's a little bit of technical glitch over here. Okay, so before I continue with the class, whosoever have joined, please note that on Monday, we are not having this particular course. Now we'll have it on Tuesday from 2:30 to 4 p.m. I'll also make the announcement again at the end of the class. But for whoever of you have joined, please note that Monday we are not having the AMC lecture. The next lecture is going to happen on Tuesday from 2:30 to 4 p.m. So please note that. Okay, now coming back to our analysis of the impedance data.
Ma'am,
So as
it's a one-time thing, or will it be
it's a
regularly on?
one-time thing. No, it's a one-time thing. It's a
Okay.
one-time thing. So it's only for the next class we are not having on Monday. We'll have it on Tuesday. Yeah. So now, so if you can see over here, this x-axis, we are having the real z, or which we write as z prime. And on the other side, we are having this imaginary z. So this is nothing but the Nyquist plot, the way we are actually getting out this EIS data. So this is how we are plotting it. So now let's see what is happening. Now another way in which you can have this data plotted is by the board plot. So this is another popular presentation method. The impedance is in this case is plotted with log frequency on the x-axis, as you can see log omega on this x-axis, and both the absolute values of the impedance, that is the mod z or log mod z, this is that is the impedance as well as the phase shift on the y-axis. This is plotted on this y-axis. So both Nyquist plot and board plot, you'll find they represent the same result. But what is the difference over here? In Nyquist plot, when I go back, if I just move back, if you see over here, when you look into this plot, you are not able to make out, what is the frequency. And if you remember, we are applying quite a lot of frequency from millihertz to megahertz. We are applying that frequency change. So when you look into the Nyquist plot, you are not able to make out that, what is the frequency in which this particular thing has been plotted. But only thing you have to remember is that the higher frequency is on the left hand side of the plot and the lower frequency on the right hand side of the plot. So you can see over here this omega is 0 on the right hand side, whereas the omega is equal to infinity on the left hand side. So please remember, in the Nyquist plot, when you are moving from to the positive direction of the x-axis, actually your frequency is kind of decreasing. So please remember that. Whereas when you look into the board plot, because you are having log of this frequency already plotted, so it is giving you an idea of the frequency as well as it. But somehow Nyquist plot is much more popular compared to the board plot, though both of them gives the same data. So whenever you're looking into any research publication, mostly you will see all the data is given in the form of Nyquist plot. So now the main thing is that, okay, fine, now I have got this particular, whatever, these different kinds of impedance I'm talking about and all this Z prime, Z double prime, all these things is fine. But how do I make out, sensible data can come out? How can I interpret the data, whatever is coming in? So for that, what we have to do is you have to commonly analyze it by fitting it to an equivalent electric circuit model. So now what are the different electrical elements which you have to fit into the circuits? These are the common ones. So you have a resistor. The impedance of this resistor, please remember, is independent of frequency and it only has real components. So when you're talking about resistor, it is going to be mostly hovering on the x-axis. Now you have something which is inductor. The main electrical elements are resistors, capacitors, and inductors. So inductors, the impedance of an inductor, it will increase as frequency increases. And please remember that inductors have only an imaginary impedance component. So it is going to be along the y-axis. Okay. And also the inductor's current is phase shifted 90 degrees with respect to that of the voltage. Resistor is always in phase with the voltage. Inductor's case, it is phase shifted 90 degrees with respect to the voltage. In case of a capacitor, what happens? The impedance versus frequency behavior of a capacitor is just opposite to that of an inductor. So a capacitor's impedance is going to decrease as the frequency is raised, and the capacitor also has only an imaginary impedance component. And the current through a capacitor is phase shifted minus 90 degrees with respect to the voltage. So please understand this thing. You have a resistor, you have an inductor, you have a capacitor. You are having all these plots coming in, all these semicircles, straight lines, all these things, whichever is there in the Nyquist plot. Now you have to fit it as per, putting in all these different electric circuit elements. Now you have another important circuit element, which is Warburg impedance. So this is a general impedance which represents a resistance to mass transfer, that is diffusion control. So now you have this diffusion of the lithium ions happening. So how do you represent that? It is given by this Warburg impedance. The impedance depends on the frequency of the potential perturbation. So at high frequencies, the Warburg impedance is really small, since diffusing reactants don't have to move very far. because at very high frequency, it's not able to diffuse very far. At low frequencies, the reactants have to move further, and so this increases the Warburg impedance. So on a Nyquist plot, this Warburg impedance appears as a diagonal line with a slope of around 45 degrees. So if you remember our first slide where I showed you, you found that at the end of it, so at the lower frequency region, you have this straight line with making almost a 45-degree angle. So that is basically giving you this diffusion coefficient, and this is the Warburg impedance. And then you have something very important, which is a constant phase element. Many of the times this fitting you cannot do using, your resistors, inductors, and capacitors and Warburg impedance. What you need is a constant phase element. What is that? Because the capacitors, whatever you have in these EIS experiments, they often do not behave ideally. So they will act as a constant phase element. So this is a very general term which is used for an imperfect capacitor. So CPs normally exhibit, instead of a 90-degree shift, somewhere a shift between 80 to 90 degree. Okay, so that is why it is called as an imperfect capacitor. So you have all these equivalent elements, and that is the resistor, inductor, capacitor, Warburg impedance, and your constant phase element. And this is how their impedance things are going to look. So in case of resistor, the Z is equal to R, whereas in inductor, it is J omega L. So this is how, you have to have these different impedance elements. So fine, now what happens is very few electrochemical cells can be modeled using a single equivalent circuit. So what you have is there will be a number of elements in the network. So both series and parallel combination of these elements will occur. And so if you have an impedance in series, then Z equivalent is a summation of all these impedances. When you're having impedance in parallel, you know how to sum them up. And please remember that resistance and impedance both go up when the resistors are combined in series, whereas impedance goes up but the capacitance goes down when the capacitors are connected in series. So all these things you have to remember when you are actually modeling your whatever data you have gotten from your EIS. So for the resistor, you see the Z prime is equal to R because you have nothing on the Y axis. So this is how it is going to look. In case of a capacitor, you have nothing on the X axis. It is only on the imaginary Z plane. So this is how the Z double prime is going to look. And if you have a resistor and capacitor in series, then this is how the plot is going to come in. So these are the common equivalent circuit models you have. Then if you have resistor and a capacitor in parallel, then you will get these kind of a semicircle, which you normally see in case of Nyquist plots. So what you have over here is something which is known as a simplified Randall cell or a simplified Randall circuit. So it's one of the most common cell models. So when you start modeling, you will put in this particular cell, and then you will keep on iterating it until unless, and then you will keep in fitting in all these other electrical elements, and then you will see how close your fit is coming to whatever data you have obtained. So it includes a solution resistance, which is this one in the solution. Then you have something which is known as a charge transfer, which is happening over here. And then what you have is a double layer capacitor, as you can see over here. So ultimately, this is the Randall cell, the simplified version of it. So this, whatever you see in this particular cell region, this is how it will look in the equivalent circuit. So this is basically the idea. And so now when you have a Nyquist plot, the semicircle, if you look into it, so what are the things you are able to find out from here? This is something which is important. You have to understand that this particular plot over here, you have a capacitance which is given by this point on the y-axis. You have a R omega over here, which is basically your coin cell's resistance, which is the internal resistance or impedance which is arising due to the assembling materials, whatever you have, your electrodes, your electrolytes. So all these interfaces going to have some kind of impedance. So that is the resistance which is coming over here. Over here, what you have is the resistance coming from the cell as well as that coming from the charge transfer mechanism. And over here, what you have is the capacitance. So this semi-cycle Nyquist plot means a charge transfer determining the cell process. This R omega and RCT can be, RCT is that is resistance due to charge transfer. It can be directly found from the Nyquist plot. And this capacitance can be calculated by value at the peak of the semicircle, whatever you are seeing. So now if you have a mixed kinetic and diffusion control, so apart from the charge transfer, if you are having a mass diffusion also happening, which is definitely there in a particular circuit, so in that case, you will have to consider, two different kinds of equations. So just this I have given for your understanding. It's not that you have to remember or anything, but this is going to help you understand the EIS better. So as of here, you can see this equivalent circuit model. This is due to your assemblage of the cell. This you have because of the capacitance, whatever is there. This is the charge transfer, and then you have this Warburg impedance coming into the picture, and this Warburg impedance, please understand, is dependent on this frequency. So now if you have an omega value which is very small, in that case what you see is a line. This particular thing is going to form this z double prime is equal to z prime minus r omega rct, and you have this entire value. So ultimately what you have is a straight line. Whereas in case the omega is very large, in that case you have something which is going to be, which is going to pertain to this particular region. So when the omega value is high, so when the omega value is very low, you have a straight line, and when the omega value is a little more, in that case you will have this kind of a look over here. So combining these two, you will get the Nyquist plot. At the high frequency range, please understand the cell process is basically determined by this entire charge transfer region, and at the low frequency range, the cell process is determined mostly by mass transfer or diffusion. And all this together is going to give rise to this plot, whatever you are seeing. So by using the equivalent circuit model, you'll be able to get in all these various impedance value, which is going to give you what dynamic processes are happening inside your cell. So EIS modeling. So electrochemical cells, this can be modeled as a network of passive electrical circuit elements, and the network is called the equivalent circuit. And the EIS response of an equivalent circuit can be calculated and compared to the actual EIS response of the electrochemical cell. So how do you model? You get the experimental data, you develop a possible equivalent circuit as shown over here, keep on adjusting it until it fits well, and then you can obtain the parameters which is related to the different elements. So with that, you will be able to get what exactly is the impedance of your cell when it is in the open circuit mode. What is it when you are starting it to cycle, how the charge transfer is happening, how your SEI layer is forming, what is going to be the mass diffusion. So all this data is going to be there for every cycle when you are recording EIS in the constant discharge and charge mode. And what are the common softwares which you will get is ZSIMP-Win. This is normally used. ZView is also used. And then you have Camry, Echem Analysis. So these are the common softwares which you'll be using for the EIS modeling. So now please understand how an ideal spectrum is going to look. An ideal spectrum is going to look somewhat like this. You will get, here I am showing you two different semicircles followed by a straight line which is making a 45-degree angle with your Z prime axis. So with the decreasing frequency, so you see your frequency is decreasing in this direction. The first feature is a non-zero ohmic resistance where your spectrum is actually intersecting with your real Z prime axis, and this is represented in the equivalent circuit by this resistor HF. Then over here, this second semicircle, what you see over here, this is represented by this particular equivalent circuit. The third one is due to this, and the fourth one is your Warburg impedance. So these are ideal spectrum of electric circuit elements, but it doesn't look like this when you are actually plotting it in the Nyquist plot. It is going to look somewhat like this as shown over here. So if I'm talking about a lithium ion battery, when I take in an EIS, this is how it is going to look. So you have this high frequency range, you have a small semicircle over here followed by a bigger one, and then what you have is a straight line. And it is definitely not showing that ideal thing. And why this is happening? Because you're having all these different processes which are not, separated. They are kind of intermingling with each other, and then that is why you see this kind of practical EIS spectra, what you get when you are actually doing an EIS for a lithium ion coin cell. So you have all these different processes taking place. So in this particular case, you see I have marked it in 4 different regions, A, B, C, and D. So now what is happening in these regions? This is what, and this is the equivalent circuit. So what you have is this RO value, which is nothing but your the entire resistance or impedance which is arising due to the different electrode materials, electrolytes, your separator, all whatever is there, whatever impedance is there in between the interface. So that is represented by this particular value, and this value is very easy to get wherever your lines crosses this Z prime line. So that is basically that resistance value. And then after that, what you have is the high frequency region B. Look into this region B. So this is represented by a solid electrolyte interface resistance, RSEI, over here, and this is how this particular equivalent circuit is going to look. So you have a SEI layer capacitance, which is this CSEI. You have a fractional element, which is this delta alpha 1 corresponding to the lithium ion migration through this SEI film layer. And obviously you have this resistance over there. Then you have a medium frequency region over here. This is basically where the charge transfer is happening. And so for that also you have a double layer capacitance happening. You have the corresponding lithium ion diffusion also taking place. And of course you have this resistance coming in. And then ultimately you are moving to the low frequency region D, and this is represented by the Warburg element ZW, as you can see over here, and a fractional element which corresponds to the lithium ion diffusion process in the active material of the electrodes. So all the processes, whatever is taking place inside your lithium ion cell, for a single discharge and charge, you're able to make out after you get out this EIS plot, and you are correspond modeling it and you're fitting it to an electric circuit. So this was about EIS, a flavor of it. Of course, when you start doing experiments and you start getting the data, you will get more and more clarity about this. But as of now, I think this is enough for this particular course. So now we move to something which is the life of a battery. So please understand that most lithium-ion batteries, how the lifetime of a battery depends on various factors. So these batteries should not be charged at ambient temperatures below 0 degrees or above 45 to 50 degrees, because then the battery life definitely is affected. So if you charge at a high temperature, it will decrease the cycle life and it will present a safety hazard. Whereas if you charge it at a low temperature, it can lead to the growth of lithium metal dendrites, and this is going to result in an internal short circuit, and it will destroy the battery and it will potentially cause fire. So batteries should be stored at or near room temperature at 20 to 40% state of charge. If you are storing it while fully charged or in elevated temperatures, this is going to put a lot of stress on the cell. It is going to reduce your battery life, and it's going to increase the amount of energy which is available for thermal runaway should an accident should occur. So please understand that the battery life is dependent on many factors. But normally what we talk about a battery life is when you are having a specific capacitance, if the specific capacitance, specific capacity. So you have a specific capacity which you have kind of designated, your battery should have this much amount of capacity ideally. But when you keep on charging and discharging the battery, what happens is it keeps on losing the capacity after a few cycles, obviously, because the efficiency is not always 100%. So gradually, because of the degradation mechanism which happens in the best of the batteries, it will start losing its capacity over time. And when it reaches 80% of the capacity, that is, no matter how long you charge and discharge it, it is not going beyond 80% of the capacity which it was initially showing. That means you have reached the end of life of that particular battery. So when we talk about a battery's end of life, we say that the specific capacity value is now below 80% of that, what was actually predicted for the battery. Now coming to a very important concept, which is energy density versus power density. As we know, for the batteries, we have good energy density. So energy density is what? It is the amount of energy in a given mass or volume, and power density is what? It is the amount of power in a given mass. So batteries definitely have a much higher energy density, as you can see over here, compared to the capacitors. If you see the EDLC, this is electric double layer capacitors. You can see the energy density which is plotted on the y-axis. So this is much less, whereas batteries have much less power density compared to that of the capacitors. So when we talk about energy storage, we have one factor which is the batteries, the other factor which is the capacitor. So all this, the plot which is used to give you an idea about the energy density and power density of all these different storage devices which is available is known as the Ragone plot. And over here you are plotting energy density versus power density. As you can see over here, the fuel cells, which we will be discussing at the end of the class, they have the highest energy density and the lowest power. Whereas if you see lithium batteries, they are having moderate energy density, power is definitely low. Whereas in case of the capacitors, what you find is they have very high power density, whereas the energy density is definitely low. So these are the different storage materials which we have. Now, please remember batteries. This is probably the last slide for batteries. From this next slide onwards, I'm moving towards supercapacitors. We'll cover a little bit of supercapacitors, but all these things which I spoke about the batteries, please understand that when we talk about battery, we mean various coin cells which are put together in series and also parallel to each other. So when I spoke about all these different voltage and stuff, so we are talking about a single lithium cell. We are talking about the single cell, whatever we are having, a coin cell. So over there, that voltage, the nominal voltage, whatever we are getting is around 3.7 volts or 3.6 volts and all. And then probably, you will find all these different places where you are using lithium batteries or you are using sodium batteries, and they are saying different voltages differently. Please understand that is basically the voltage which is coming in from the battery pack. It is not from the cell. So when I'm talking about a single cell, this is the maximum voltage you can get. And when you're talking, we are seeing in different batteries, it is working in 10 volts, it is working in 30 volts, it's working in 50 volts. So those are basically battery packs. So those are battery packs, and so then the voltage is kind of added up, as you know, when you are putting in all these particular cells in a series. So battery pack has various numbers of these coin cells to give you that output voltage and to give you the current as per the load which is attached to that particular battery pack. So understand this thing, and whatever we have discussed is basically the material which is being used, the electrodes, electrolyte, separators, collectors, these are in the single coin cell. So please be clear about this particular distinction. So now we move to something which is supercapacitors, which has lower energy density but very high power density. So this is also another very important storage techniques. And this electric double layer capacitor, only capacitors has been known for a very long time. And this was noticed in 1957 by General Electric. And then in 1978, the Standard Oil of Ohio gave the licensing to the National Electric Corporation, and this product was marketed as a supercapacitor. So what is basically supercapacitor? So normal capacitors, capacitance is the ratio of the stored charge by voltage. C is equal to Q by V. That we know. I think right from our 12th standard we know this. 11, 12. We have read about this, right? So now the capacitor principle is what? The C is normally experimentally how you get it out is basically you have these conductive plates which is having area of A. You have a dielectric material which is put inside in between these conductive plates, and the distance between these plates is given as D. So this capacitance value you will get as epsilon R epsilon OA by D. So A is the area of these plates, D is the distance between the plates, and epsilon R is the relative static permittivity, which is the dielectric constant. E0 is the permittivity of free space. And so you get the energy which is stored in this capacitors as half CV square, where C is the capacitance and V is the voltage value. And also you can get the power, which is the rate of energy delivered per unit time. And this is dependent on something which is known as the equivalent series resistance of these particular capacitors. So now if we look into it, what do we mean by the supercapacitors? So the energy storage in the supercapacitors is mainly in the interface between the electrodes and the electrolytes. And this energy storage method, it has a great relationship with the electrode material used. Now, rather than going into all these other things, what is written, let's look into this diagram which is given below, this particular plot. So one side I have written capacitors, and the other part you see I have written supercapacitors. So capacitors are whatever I showed in the first slide. Basically, you are having two charged plates and you are having a dielectric material in between, and then you are with that you are storing your energy is stored in that dielectric material and in between those plates. When you are having a supercapacitor, you look what we are doing. We are basically providing a lot of area. C, we saw that C is equal to epsilon R epsilon 0 A by D. So obviously, if I want to increase the capacitance of any material, I have to increase A as much as possible, and D should be decreased as much as possible. So the decrease in D though is definitely something which is finite. But A you can increase. How you can increase that A? This is by use of these kind of electrode materials. As you can see, you are using a lot of these carbonaceous materials which have a lot of porous surface. You can use a lot of porous oxide materials. They have a lot of porosity in them. With the porosity comes a lot of area, and so your capacitance is increasing. So the basic principle of supercapacitor energy storage is to store electric energy through the electric double layer capacitance formed by the charge separation on the interface between the electrolyte and the bath solution. So supercapacitor can achieve higher capacitance because of the thinner dielectric and higher surface area of the electrodes. That is why it is known as a supercapacitor. So supercapacitor will store more charge with a capacitance in the farad range, and they will store much more energy than the electrolytic capacitance. They have a very low leakage current, and they are suitable for many applications, and they generally operate within the voltage range of 1.8 to 2.5 volts. The life of a supercapacitor is around 10 to 20 years, but the capacity can be reduced from 100 to 80% after about 8 to 10 years. But you can still use it, but the lifetime goes on up to 20 years. But after 10 years, probably the capacity decreases from 100 to 80%. So now there are various type of supercapacitors depending on the mechanism. So you have this electrochemical double layer capacitors, which I showed in the previous slide. The mechanism is electrostatically ion adsorption desorption at the interface of the electrode and the electrolyte. So this is an electrostatic mechanism. Whereas on the other end, you have the pseudocapacitors. So here what happens is reversible Faradaic redox reaction between the electrolyte ion and the electroactive material. So this basically stores energy by Faradaic reactions, Faradaic redox reactions, whereas in case of the electrochemical double layer capacitor, what you have is an electrostatic ion adsorption desorption, which is giving rise to the charge storage. Now in between them lies the hybrid capacitors. So you have an electrochemical double layer ion adsorption desorption on one of the sides, and the other side you're having a reversible Faraday equation. So one electrode is EDLC, the other electrode is a pseudocapacitor, and when you combine both of them, you can have these kind of hybrid capacitors. This is the taxonomy of supercapacitors. So now let's look into the charge storage system. So this first what we are discussing is the electrochemical double layer capacitors, which is EDLC. So they store energy, as I said, using ion adsorption. There is no Faradaic or redox reactions. It's a very high specific surface area electrode, so mostly carbon is used. So if you look into this particular electrode, if you look, this is a carbon cluster, and you have all this electrolyte over here. So you have the solvated ions coming in, you have a Helmholtz double layer getting formed, and so there's a lot of surface area, and that is why your capacitance is very high. So you have this, you can model this particular thing using various model structures. So you have this Helmholtz double layer model, which states that two oppositely charged layers form an electrode electrolyte interface, and this is separated by an atomic distance, so d value becomes very less. Whereas in the other model which you can use is the Goy-Chapman model. And so here it recognizes two regions of ion distribution. So you have an inner region, and then you have, which is the stern layer, as over here you can see, immediately, which is lying just very close to the electrode surface. So this is the stern layer. And whereas you can have in the bulk solution, as you move out from this electrode surface, what you have is this diffuse layer. So the total capacitance, whatever you see, is the double layer capacitance is a combination of both the Helmholtz layer as well as this diffusion layer. So, and you can see that the electrolyte also plays a very important role. If you have a non-aqueous electrolyte, in this case, the capacitance value is between 100 to 120 farads per gram. Whereas if you use an aqueous electrolyte, then because the conductance value is very high in this case, so you have a capacitance value of 150 to 300 farads per gram. So if you look into here, look over here, if you see the type of electrolytes which you can use aqueous electrolyte, you can use organic electrolyte, or you can use ionic liquids as electrolyte. So as you differ the electrolyte, what happens? The electrolytic window changes. For aqueous electrolytes, the electrolytic window is less than 1 volt. Whereas if you are moving towards organic electrolytes, it is between 2.5 to 2.7 volts. Whereas in ionic liquids, it is between 3 to 6 volts. So, and the viscosity also changes. Then your ionic conductivity also changes. And along with it, you have all these different assembling techniques. So in case of aqueous electrolyte, you can assemble these capacitors in the ambient atmosphere. Whereas when you are having organic and ionic liquids, then you have to move into inert atmosphere. So obviously the cost differs, the toxicity differs. Your ion size of this electrolyte is going to differ. And that will again make you understand that where you can use these different kinds of electrolytes. So mostly the aqueous electrolyte is used in case of pseudocapacitors. Whereas organic and ionic liquids, they are not used for the pseudocapacitors. So aqueous electrolytes are which ones? You can have sulfuric acid, which is an acidic electrolyte. You can have potassium hydroxide, which is a basic electrolyte. So they all have low cost. They have very high ionic conductivity. But the drawback is obviously it has a low potential window. And this acid and alkali, it is going to corrode all these current collectors, whatever you have. So an important consideration when you're selecting an electrolyte for porous material is the size of the electrolyte ion, because that electrolyte ion size, if it is it is larger than the pore size, then obviously it is not going to infiltrate into the pore. So the advantage which you are going to get putting in, increasing the surface area, that you are not going to get if you are having an electrolyte ion whose size is more than the pore size. So that is an important consideration to remember. In case of the non-aqueous electrolyte, the advantage is obviously you have a higher operating voltage. Cost is a little bit, it's going to be a little costly compared to your aqueous electrolyte. And another very big drawback is the lower ionic conductivity. So now let's look into, all these different electrode materials like activated carbon, you have templated carbon, you have CNT, you have carbide, which is derived from carbon, carbon blacks or aerogels, whatever you have. You look into the surface area. And then you see if you're having activated carbon within the surface area of 1000 to 3000 meter square per gram, if you are using different electrolytes, you just see how the capacitance value changes. So if you are having activated carbon and you are using an aqueous electrolyte, you find that the capacitance value is going to be higher than what you get in case of organic or this. Whereas if you have carbide derived carbon, in that case, whether you are using an organic or ionic liquid kind of electrolyte, what you find is that the capacitance value remains more or less the same. So for every type of material, you need to check it with, with, if you are changing the electrolyte, you will find the capacitance can either improve or it can go down. So this is a very active field of research. Pseudo capacitor, whatever we discussed was the EDLC, where you are having this electrical double layer capacitors. So the other form is the pseudo capacitor, where you are having this Faradaic or the redox reaction happening. So this is utilizing fast and reversible redox reactions at their surface. So what is happening over here is there is an electrochemical charge transfer process which is taking place. And this is limited by the finite amount of active material or the available surface. So what are the materials which is going to give you these kind of pseudocapacitance? It is mostly the family of conducting polymers such as polyaniline, polypyrrole, or the derivatives of this polythiophene. And also various transition metal oxides. They are very good pseudocapacitor materials, like ruthenium oxide, manganese dioxide, lead dioxide, nickel oxide, Fe3O4. So all of these are very good pseudocapacitive materials. And also carbon materials can also be used for pseudocapacitors, provided you have some heteroatom doped onto it, or you have some other functional groups which are present on the carbon. If you have that kind of carbon material also, that can also show pseudocapacitive behavior. So please remember that while double layer capacitors, they store energy on the surface of the material, these kind of capacitors, they will store charge throughout the entire volume and via fast doping, de-doping exchange of ions, and hence the amount of energy that can be stored in these kind of capacitors is generally higher than what you see in EDLC type of materials. And also the Faradaic reactions, they lower the self-discharge. So if I look into a pseudocapacitor, you just see the capacity over here. If you have a metal oxide like ruthenium oxide, which is being used as a pseudocapacitor material, then the capacity is around 1300 farads per gram. In case of conducting polymers, you'll find the capacity is definitely much low. And if you're combining both of this, then also you will find a lot of capacitors which can be used combining both of this, and they will also have a good, very high capacitance value. So this is a kind of work which has been kind of reported over here, where you are improving the voltage window using bismuth oxide and polyaniline composite electrodes. Very recent work where these kind of capacitors have been used, and they have been used to kind of illuminate various kind of devices, as you can see over here. So this is a very hot field of research which is going on. Then you have something which is known as an asymmetric capacitor. What is that? This is a hybrid supercapacitor. So what is happening? You have an EDLC type absorption electrode on the others on one side, and on the opposite side, the counter electrode is basically a pseudocapacitor. So one side you are having double layer capacitance, the other side you are having pseudocapacitance. So you have to understand that you cannot just combine anything with anything. So some kind of groundwork has to be done when you are doing these kind of combination or hybrid capacitors. So this Faradaic and the non-Faradaic electrodes, they has to be selected, which has high charge discharge rate capability. Then also you have to remember that their potentials should be close either to the low or the high end of the operating voltage window. Okay, it cannot be having too much gap between its potential window. And then You have to understand the Faradaic electrodes, they have much higher capacitance compared to the non-Faradaic. So if you have to balance both of them, then in that case, you have to use the non-Faraday component on a larger extent compared to the Faraday component. So if you have the ratio of the non-Faraday to the Faraday component, then it should be as low as possible. The non-Faraday to the Faraday component should be as high as possible, because non-Faraday one is having lower capacitance compared to the Faraday electrode. So you have to balance the active mass of the two electrodes, usually by using a thicker or a dense non-Faradaic electrode. And the non-Faradaic electrode should have highest possible electronic conductivity, surface area, as well as porosity. So all these factors have to be taken into consideration whenever you are having a hybrid or a hybrid capacitor. So now if you compare a rechargeable battery versus a supercapacitor, the charging time of for a capacitor is going to be in seconds, whereas in case of a battery, you know, it is going to be in hours. The discharge time for a capacitor is short, so it gives you huge burst of energy at a very short time. And whereas in battery, it will give you a less amount of energy, but it is going to extend. The discharge time is going to be longer, but it is going to give you a fairly rapid amount, good amount of energy over a longer period of time. Then charge discharge cycles in case of a supercapacitor extends to almost a million cycles, whereas in case of a battery, we go up to 2000 to 5000 cycles now for the very good battery packs which are coming in. And if you just give a very layman's example, supercapacitor is that like for a 100-meter race, the amount of power you put in that 100-meter race, whereas in case of a battery, it is more of a marathon or who is running a marathon. So you need a lot of energy and you have to go for a very long time. So that is how you can distinguish it. So what are the different applications of supercapacitors? We spoke a lot about energy storage. We know a lot where batteries are used. So where is supercapacitor used? It is used for all these uninterrupted power supply devices. It is used as lightweight power supplies for very small aircrafts. It provides short duration power for various vehicle systems such as in braking or in steering. Then you it can be used to absorb power which is generated during regenerative braking, and it can extend the range and the battery life in hybrid electric vehicles. So that is also a very important application of the supercapacitors. So currently, you know, in CSIRO in Australia, this is the National Science Agency of Australia, it has developed the Ultra battery, which is combining a supercapacitor and a lead acid battery in a single unit. So it has 4 times longer the life cycle, 50% more power, 70% cheaper than batteries, which are normally used in hybrid electric vehicles. So this is a very important, advancement in supercapacitors, what you can say. And it has lot of applications in various kind of energy storage technologies. Then we are coming to the last part, which is fuel cells. So what is a fuel cell? This is, if you remember, when we showed you the Ragone plot, when I showed you the Ragone plot, fuel cells was lying something which is having the highest energy density. The power density is definitely the lowest, but it has the highest energy density. It has much higher energy density compared to that of a battery. So what it is, it's an electrochemical device that is converting chemicals, hot chemicals like hydrogen and oxygen into water, and it is producing electricity in the process. So as long as these reactants, that is hydrogen and oxygen, is supplied to the fuel cell, it will produce electricity and never go dead, unlike conventional batteries, because conventional batteries has finite active materials in it. In this case, you are flowing hydrogen gas through one of the electrodes, flowing oxygen gas through one of the electrodes, it is combining, it is giving you water, and the electricity is generated in the external circuit. So this is the ideal kind of energy generation thing which we strive for, which looks very easy on paper, but it is very difficult to achieve practically. So what exactly is the concept over here? So you have the anode where hydrogen is moving in, you have oxygen where the cathode is, and then what you are generating, the byproduct is only water, which is very safe, and what you have is the electricity which is moving, or the electrons flow which is happening in the external circuit, and you're getting a DC current which is getting generated. Okay. So a fuel cell uses the chemical energy of hydrogen or other fuels to produce electricity in a clean and efficient way. If hydrogen is the fuel, the only products are going to be electricity, water, and heat. So see what are the advantages. Huge amount of advantages are there in fuel cells. So it is obviously going to reduce your greenhouse gas emissions. It is going to reduce oil consumption. It is going to expand the use of renewable power. How? Through the use of hydrogen, which is derived from renewable resources as a transportation fuel, as well as for energy storage and transmission. Highly efficient energy conversion is possible over here. You can have fuel flexibility. Instead of hydrogen, you can use natural gas, you can use biogas, you can use methanol, and dependingly, you will name the fuel cell. It has reduced air pollution, criteria pollutants, water use. It's highly reliable grid support. So it also has a very quiet operation, low maintenance needs, and high reliability. So these are the lots of advantages of the fuel cell. But practical difficulties are there. So what is the difference with battery? Fuel cells will require a fuel to flow in order to produce electricity, and this heat is produced from the chemical reaction and not from combustion. So you see there are different types of fuel cells which are there. One is the proton exchange membrane. There is direct methanol fuel cell where methanol is being used as one of the fuels. Alkaline fuel cell you have phosphoric acid fuel cell, you have molten carbonate fuel cell, and then you also have this SOFC, which is the solid oxide fuel cell. And these last three, the phosphoric acid fuel cell, molten carbonate fuel cell, and solid oxide fuel cell, they are all suitable for microgrid applications. Okay. So you can have these various kind of hydrogen fuel cells where hydrogen is basically used as a fuel. So in this you have this proton exchange membrane fuel cell, you have this alkaline fuel cell, and also you have this phosphoric acid fuel cell which can be used as a hydrogen fuel cell. Then you can have hydrocarbon fuel cells, and in this case, as the name suggests, the fuel is a hydrocarbon. So you can have direct methanol fuel cell, you can have direct ethanol fuel cell, and you can have all the biofuel cells also, which is again, you are using different kinds of methanol fuel cells or ethanol fuel cells. So these are the different types of fuel cells which are there, on which research is going on. So what exactly is this idea? We are saying hydrogen moving in, high oxygen moving in. So what is actually happening over here? So please understand what you have is two different electrodes over here. How we are preparing the electrode, that is different. But first you must understand what is happening. You are having a membrane in between these two electrodes. Right across the membrane, you have something which is very important when you talk about fuel cell, which is the catalyst layer. The catalyst layer, tremendous amount of role in fuel cell. And this you can say is the major bottleneck. You need to have very good catalysts to have this kind of efficient hydrogen movement and oxygen movement coming in from the air, and the generation of this catalyst layer is actually very important over here. Then you have a gas diffusion layer, and then you have these porous electrodes. Okay. So what is the catalyst layer? At the interface of the membrane, there are layers with catalyst particles. Platinum catalyst supported on carbon particles. So immediately you can understand there's a lot of research going on in catalyst materials, because platinum to be used as catalyst for thousands of years is going to be a very expensive affair. So a lot of research is going on catalyst materials, because how you can reduce the use of platinum, and you can use more and more earth abundant materials with good catalytic activity. And then you have these gas diffusion layers, which is a polymer membrane with catalyst layers, which is settled on both the sides. And this is sandwiched between two sheets of porous layers, which is called the GDLs. So this is generally made out of, or the gas diffusion layer. GDLs is nothing but gas diffusion layer. And this is going to allow the diffusion of both reactant gases and the product, which is water in this case. So this perform as electrically conductive electrodes and the heat conducting medium. So it has a dual purpose. It is going to act both as an electrically conductive electrode, and it is also going to act as heat conducting medium. So this membrane, this catalyst layer, and the GDLs all combined together is something which is known as the membrane electrode assembly. Okay. So how the fuel cells operate? So in case you have a proton exchange membrane fuel cell, the hydrogen atoms electron and the proton, as you see over here, this is separated at the anode part of the material. Okay. And then what happens? Only this protons is going to move through this proton exchange membrane and is going to move into the other side. And the cathode part, what you're having is the oxygen which is coming in. So this proton is going to react with this oxygen, and it is going to give rise to water. And on the external circuit, you will have this electron moving in, and what you get is the DC current. So this is basically how a fuel cell operation happens. And this particular potential at which this reaction should happen is at around 1.23 volts. But definitely what happens is you need to have, there is an over potential which is there always. So the ideal voltage is 1.23, but whenever you are using a fuel cell, it will the open circuit voltage you will get is around less than what actually it should supply. And the difference between this real open circuit voltage and the ideal output voltage, it is caused by factors such as crossover of the reactance. So the curve that characterizes the relationship between the voltage and the current, as you can see, voltage and the current, and this is the plot what you get, and this is known as the polarization curve. So why this loss? Actually, it should be like this, right? With the current density, the voltage should be constant. But what you see is that you see this kind of a drop which is happening. So what is this? So you have these three different loss making mechanisms which is there. One is activation loss over here. Then you have something which is known as ohmic loss. And then you have something which is known as the concentration. So what are these losses? Activation loss. And this is the part of the voltage which is lost in driving the chemical reaction. Okay. So this losses, so when you are having this chemical reaction, this loss is happening because to drive the chemical reaction, you are losing this voltage. And this is because of the catalyst material and the microstructure of this entire electrode assembly, whatever you're having, then the reactant activities, and it also depends on the current density. So all of this contribute to this loss, which is known as the activation loss, which is the severe loss which you see at the very beginning. Then you have something which is known as the ohmic loss. What is an ohmic loss? This is the voltage loss which is caused by the resistance associated with the electrodes, electrolyte, and other interconnections. So wherever there is any interface happening, there is going to be a resistance over there, and all these resistance combined together, they contribute to this ohmic loss. So this is proportional again to the current density. Besides the material and the structure of the fuel cell, the temperature also impact these kind of losses. So ohmic loss happens because of all the materials which is put together to assemble this fuel cell. And then you have something which is concentration loss. Why this concentration loss? Because again there is some diffusion happening. Why this diffusion happening? Because you're having some charge getting transported from one side to the other. So there is a loss which results from the drop in concentration of reactants at the surface of the electrode, and it depends strongly on the current density, the reactant activity, and also on the electrode structure. So there is going to be a drop in concentration of the reactants at the surface of the electrodes, and that is the reason why you will have this kind of concentration losses which comes in at the different current density. So as the current density increases, you can see that which type of loss is actually playing a big role. So when you have a low current density, in that case, it is mostly the activation related losses which is happening. When you have the current density in the medium range, then what you see is all this ohmic loss. Whereas when you are talking about a very high current density, then what actually you will get is a lot of this concentration losses happening. So voltage loss as in a practical fuel cell. And this is a very interesting slide over here. So this is basically giving you on the absolute left-hand side, you see what is the name of the fuel cell. So you have solid oxide fuel cell, you have this MCFC, you also have this alkaline fuel cell, you have the phosphoric acid fuel cell, you have the methanol fuel cell, and then you have the PMFC kind of materials also. So what is the fuel when you have SOFC? It is hydrogen and carbon monoxide. The oxidizer is of course oxygen and air. And the electrolyte which you use is a solid oxide ceramic electrode. And you see the temperature range in this particular fuel cell can work, which is around 600 to 1000 degrees centigrade. Whereas when you are having this MCFC, this is a molten carbonate fuel cell, in that case, the fuel is the same. It is hydrogen, or you can use carbon monoxide. And the oxidizer is carbon dioxide, oxygen, and air. Here, the electrolyte is a molten carbon salt. And this particular MCFC, you can use at a temperature range between 620 to 660 degrees centigrade. Then you have, which is known as the alkaline fuel cell. As the name suggests, the electrolyte in this case is an alkali, which is potassium hydroxide. The fuel is hydrogen, the oxidizer is oxygen or air, and this works in the temperature range between room temperature to around 250 degrees centigrade. Then you have the phosphoric acid fuel cell. Phosphoric acid is the electrolyte, as the name suggests. This works in a temperature range of 150 to 220 degrees centigrade. Fuel is hydrogen and oxidizer is oxygen. Then you have this methanol fuel cell. So in this case, what is happening? You're using methanol, which is the fuel. You're using oxygen and air as the oxidizer. And you have a perfluorosulfonic acid membrane, which is being acting as the electrolyte over here. So this is, you have a membrane and you have this electrolyte, which is basically an acid, which is the protons. And this particular acid membrane, it allows the movement of this proton between the anode and the cathode. And then you also have PEMFC. And in this case also, again, you have a proton exchange membrane over here, which is a perfluorosulfonic acid membrane. It allows the exchange of proton. And here you are using hydrogen as a fuel and oxygen or air as an oxidizer. So these are the different types of fuel cell. So the same thing has been given over here, these different types of fuel cell, their names and how, which temperature it is operating in. So if you look into a proton exchange membrane fuel cell, this particular fuel cell, you see the electrodes, that is the anode and the cathode, it is separated by a polymer membrane electrolyte. This is that yellow thing which you see over here. This is the PM or the proton exchange membrane. Each of the electrodes is coated on one side with a thin platinum catalyst layer. So you have this catalyst which is coated on one side of the electrodes. The electrodes, catalysts and membrane, they form this MEA or the membrane electrode assembly. Hydrogen and oxygen are supplied on either side through channels formed in the flow field plate. So you can see all these flow field plates which are there, and from these plates basically your hydrogen and oxygen is flowing in through the gas diffusion layer, then it is coming into the catalyst layer, and then you are having this exchange of proton which is happening, and it is going and moving and it is reacting with the oxygen on the other side, and the byproduct is water, and on the external circuit what you get is the flow of the electron. So this is how a PEMFC functions. The same thing, if you look how it is going to look, that is for the PEMFC, whereas if you have a solid oxide fuel cell, then what you have over here, what you have is the anode, and the fuel is hydrogen and carbon monoxide. So when you are having this particular fuel over here, you are actually having water, steam, and you are having carbon monoxide being passed through it. Ultimately, it is generating hydrogen and carbon dioxide. So the hydrogen is kind of moving in through this permeable anode, and you're having this impermeable electrolyte. This is the solid oxide material which you have. So this is the impermeable electrolyte over here. Then again, you have a permeable cathode from which oxygen is coming in. And ultimately, what you have over here, that oxygen from the air, it is flowing through the cathode. A fuel gas which contains hydrogen, such as methane, it flows past the anode. Oxygen ions are migrating through the electrolyte and it reacts with the hydrogen to form water. Water reacts with the fuel to form carbon dioxide and hydrogen, and electrons from the electrochemical reaction flow from anode to cathode through an external load, as you can see over here. So this is a SOFC. So what is this advantage of the fuel cells? Obviously, it has very high efficiency. It is modular in nature. It is quiet. It is non-polluting. There is no emission of all these greenhouse gases. It is distributed. It is combined heat and power, and it is also very load flexible. So right now, fuel cells using methanol and oxygen are being developed, and they are also being extensively used in the space program as a source of DC power, direct current power. They are very efficient, capable of providing hundreds of kilowatts of power. So if you can look into the fuel cell applications as of now in stationary power systems, where you can use these fuel cells in residential applications, in combined heat and power systems, and in distributed power generation. You can also use it for transportation applications in cars and in buses, in portable fuel cells, mobile phones, laptops, and UPS. These are all very futuristic as of now. And of course, what is already being used is in the space applications. So these are the probable applications. So once we are able to kind of really fix in this particular technology, it is going to have a lot of energy density and a lot of applications, as you can see. So we will stop the class over here. If there is any question, you can just come forward with your questions.
Hello.
Hello.
Ma'am, my question is that since the composition of the batteries and the fuel cells is so radically different, do they
Yes.
share any common misgivings or common problems to overcome, or are they completely different in that regard as well?
Common problems, See, the thing is that in case of the fuel cell, as you can see, the scientific problem over here is getting good catalyst. As you know, this oxidation, the reactions over there is mostly catalyst dependent. The efficient catalyst, more efficient catalyst, and more efficient membrane, you will be having a better fuel cell over there. Whereas in case of batteries, it is mostly dependent on the materials, whatever the active materials, whatever your thing. So common problem, as you can see over here, it is an electrochemical energy storage only, but there is no common problem as such. We cannot say it's a common problem. The thing is that how better efficient material you can get, how you can fabricate a much more efficient device. So that is the idea. So the energy storage is all electrochemical in nature, but how you can fabricate a much more efficient device is what every researcher in the world is looking into.
Okay, ma'am.
In case there are no further questions, then we end the class today and we will meet on Tuesday. Please remember, again, I am repeating, Monday there is no class. The next class which we are having, or the next lecture, will be on Tuesday from 2:30 to 4 p.m. So whoever is present in the class, please let your other fellow members also know the same. Thank you. Have a good evening.